All right, hello everyone. Welcome to the Marshall W. Allworth Planetarium. My name is Jessica. I am the director and will be your guide to the bizarre things in space tonight. You've also met Spencer, one of our students who is helping out tonight. But yeah, for the show, Beyond Bizarre, Strange Things in Space, we're going to be looking at some really cool things. Some of the mysteries we have kind of solved. Others are still big old question marks, but we'll go through all of that. If at any time during the show you need to leave, that's no problem. You'll just exit through the same door, which I will close in just a second so we can get nice and dark in here. And if you have any questions throughout the show, feel free to ask. I can't really see raised hands in the back, so you're welcome to just ask your question out loud. If you're not comfortable doing that, you can always come see me after the show and ask questions. But I think that's it for my intro spiel. So I'm going to close this door and head to the back and we'll get started. All right. Now, as I said, with Beyond Bizarre, we are going to be looking at strange things in space. And we're going to start off with a few things in our own solar system, then a few things in our galaxy, and then a few things with galaxies. So kind of start close to home and then slowly move to mysteries further and further out. So we are going to get started over at Saturn. Now, if you've seen any of the gorgeous Cassini images of Saturn, you may have seen some weird pictures of Saturn's North Pole, because there is a hexagon circling around Saturn's North Pole. Now, we did actually know about the hexagon before Cassini. We got glimpses of it when Voyager 1 and 2 flew past Saturn in 1980 and 1981, respectively. But Cassini was the first spacecraft to give us a full-scale image of this hexagon. And when I tell you this hexagon is big, I mean it. One side of the hexagon is bigger than Earth. This thing has winds swirling around at several hundred miles per hour. Each side is about 9,000 miles long. It's a massive hurricane, we think. But it's a hexagon. How do we get a hexagon-shaped storm naturally? And that's been the big puzzle. We've kind of answered it a little bit. It turns out that if you have air flowing at different speeds, those different speeds of the air can interact and create polygons, shapes with sides. So here's a simulation that was run that has, and it's going to start off with numbers. You don't need to worry about the numbers. But we have this circular tank. They used fluids, like a liquid, but this works for any fluid, whether it's liquid or gas. But if you have those fluids spinning at different speeds, they're going to interact and create these like eddies, these little vortices. And those vortices are going to want to space themselves out evenly. And with that, you can get polygons. They got anywhere from 3 sides up to 8-side shapes. And to get a 6-sided hexagon, you just have to have certain parameters to make that happen. So we think this is what's going on in Saturn's North Pole. Now, there are a couple of other mysteries that are still afoot, though. One, Saturn's South Pole doesn't have a hexagon. So why does the North Pole have one, but the South Pole doesn't? The other question is how this has lasted for so long. hurricanes and any sort of air feature, jet streams, streams of air, whatever, they typically aren't long lived, at least not here on Earth. So, why are they long lived on Saturn? Why has the shape been around for a couple decades now? We don't have the answer to those questions. And sadly, Cassini is no longer with us. Its mission ended, I believe it was 2017. I believe that's right. I blocked it from memory because it was very sad. In its final days, though, it was decommissioned by flying into Saturn. So in its final days, as it slowly spiraled closer and closer into Saturn, it continued to send back data and images. And astronomers are still going over all of that data and hoping that that information will help give more insight into this weird hexagon on Saturn. All right, well, that's one mystery down. Let's head on over to our next object in our solar system. This time we're going to head over to Jupiter, but specifically we're visiting one of Jupiter's moons, Io. Now, here at the planetarium, we have a nickname for Io. This is the pizza moon, because it kind of looks like a pizza a little bit. But all of those dark spots you're seeing are volcanoes. Io has over 400 active volcanoes. That's more than anything else in the solar system, even Earth. Io is so volcanically active that anytime a spacecraft has flown by, it has gotten pictures of active eruptions. Now, we consider Earth to be volcanically active. More so maybe right now with all of the things going on. We got the Iceland, Mexico volcano. I forget the other one. There's a few other kind of stirring up right now. But in the grand scheme, volcanoes don't erupt that often on Earth. If you were to have a spacecraft just quickly fly by Earth, more likely than not, it would not capture a volcanic eruption. The fact that spacecraft not only capture one, but multiple every time they fly by Io is insane. In addition to capturing volcanic eruptions, as you can see on the two side images, we've also got lava flows across the surface. Now, volcanoes themselves, having something volcanically active, that might not seem bizarre. You're probably wondering, why the heck are we talking about this now? Here's the strange thing. Why are we still rotating? Hold on. Come on, there we go. Io is just a little bit smaller than our moon. And our moon is not volcanically active. That's to be expected. In order to have volcanic eruptions, any sort of geologic activity, you need heat inside of the world. Earth is still pretty hot. That's why it's active. Smaller objects like our moon used to be hot billions of years ago, but because they're smaller, they cooled off faster. And you know that from experience. Small things cool off faster than big things. Io should also be cooled off. It should not still have any heat to drive these volcanoes. So something else must be going on to make Io so incredibly active. And turns out the culprit is Jupiter himself. We're going to turn to see right now. Yeah, Jupiter's the problem. Or solution, whichever way you want to picture that. So you have Jupiter, and I'm just going to bring Io over. Whoops. Come on. Bring Io back into view over here. You have Jupiter on one side of Io, tugging Io towards it. Then on the other side, you've got Jupiter's 93 other moons tugging Io back the other way. So Io's caught in this tug of war. And that tug of war is changing as it orbits around Jupiter. Sometimes it's tugged a little more, sometimes a little less. So this moon is constantly being stretched and then released and stretched and released. And each time it stretches and releases, the rocks rub against each other. And just like you do on a cool morning to warm up your hands, and you rub them together, as those rocks rub together, they create heat. And this tug of war, stretching back and forth, is so extreme that it generates a tremendous amount of heat and energy. And the best way for it to escape is through volcanoes. And that's how we end up with a moon with over 400 active volcanoes, even though it's smaller than our moon. And that's what gives it the color. That yellow color is from sulfur, released by all the volcanic eruptions. All right, for our next stop, we're going to head out of our solar system, but we're going to head to another solar system. We are headed over to the star 55 Cancri, and in particular, one planet around it, 55 Cancri E, also known as Janssen. Now, this planetary system is about 41 light years from Earth. A light year is the distance that light travels in 1 year. That's about 6 trillion miles. This planet is comparable to Earth-sized. It's about 2 times bigger than Earth, but it orbits much, much closer to its star than Earth does. In comparison to Earth taking a year, an Earth year, to complete an orbit around our sun, 55 Cancri E completes one orbit around its star every 18 hours. It is really, really close. And being so close means the temperatures are going to skyrocket. Temperatures on the surface of this planet are expected to be almost 5,000 degrees Fahrenheit. So on the surface, it's expected to be a lava world, or at least the side of the planet that's facing its star, getting all of that heat, should be a lava world. Now, if you paid attention to the title, you would have noticed that I called this the Diamond Planet. That's because of what we think might be happening inside of 55 Cancri E. This planet, we believe, has a bunch of carbon, and that carbon is going to be under extreme pressure inside of this massive planet. So some estimates say, some models suggest that that carbon could get squeezed into diamonds. And as much as a third of the planet may be diamonds. Hence its nickname, the Diamond Planet. Now, there are contradictory models that don't suggest diamonds form inside this planet. But since we have no conclusion one way or the other, I'm going to continue to think of it as a giant diamond planet because I think that's way cooler. And definitely fits the bizarre, strange things in space, in my opinion. All right. Our next stop in our galaxy is one more planet. We are going to head over to the star system K2-18. Now, I know these don't have great names. They're catalog names for the discovery. Everything gets a really boring catalog name. But this star system, K2-18, has 2 planets. B and C. And K2-18b, we believe, is in the star's habitable zone, or Goldilocks zone. What this means is it's the right distance from its star for the temperatures on the planet to be similar to Earth. They would be just right to allow liquid water to flow on its surface. Now, the planet itself, K2-18b, is considered a super Earth. It's about twice the size of Earth. 55 Cancri E is also a super Earth. I forgot to mention that because it's also about twice the size of Earth. So yeah, when we first discovered this planet, seeing it Earth-sized and in the habitable zone, in the Goldilocks zone, where temperatures could be similar to Earth, we thought that we had found an Earth-like planet, a maybe new Earth, new home. It's a little bit far away. It's 124 light years, so not something we can really easily get to, but just knowing that there are other Earths out there is very exciting. Now, the fact that we found a possible Earth-like planet is in itself not the bizarre thing. Because as it turns out, we estimate that there are about 20 billion Earth-like planets in our galaxy. What's strange about this one is what we found out after we discovered it. Because new data, new measurements of this planet showed that it had a super thick hydrogen atmosphere, which would make it more like a Neptune instead of an Earth. So it might be a mini Neptune, which would make it a planet not like one that we have in our solar system. Then follow-up measurements from the James Webb this year suggested that not only does it have a thick atmosphere, it might actually have just an entire ocean covering the entire surface of the planet. It might be a water world. But with that thick hydrogen atmosphere, we don't know how hot that ocean would be. That ocean could be way too hot for any life to survive in. And that's what leads us to our kind of mystery, is what once started out, we thought, as a wonderful potential Earth 2.0 has become this very strange planet that we have no equivalent of in our solar system. And we haven't quite been able to nail down exactly what it's like there. And I personally just think it's cool. So I wanted to include it in the show tonight. All right. We are now going to head away from planets and planetary systems. And we're going to go take a look at a nebula. Now, a nebula is a giant gas cloud in space. There are lots of them. Our galaxy is full of nebulae. The one we're going to take a look at right here is the Red Rectangle Nebula. It's a weird one because of its shape. It is very geometric, very polygon, and just not what we see out of nebulae. So the Red Rectangle Nebula is what we would call a planetary nebula. It has nothing to do with planets. It's a little bit of a misleading name, but it's the result of the death of a small star, a star, about the size of our sun. Now, typically, planetary nebula, I'm going to bring up two pictures, look like either of these. They're more spherical. Because what happens is as the star is at the end of its life, it starts to puff up and blow off its outer layers. And since the star is, spherical, that gas tends to be blown out in a sphere, and you get more circular, spherical shapes to the planetary nebulae. So it is still trying to be understood how you get a rectangular shape from this. One of the leading hypotheses is there might be a really dense, dusty disk around the star, which causes the gases to be shot out, either up or down, and it kind of funnels the material in those two directions rather than all the way around. We are still trying to figure out, though, exactly how you get this shape rather than a more spherical shape. All right, the last stop in our galaxy is going to be out on the outskirts of our galaxy. We're going to take a look at Omega Centauri. Omega Centauri is what we call a globular cluster. So it's one type of star cluster. Globular clusters have tens to hundreds of thousands of stars in them. They're packed really close together, really dense, and they look like a glob of stars, hence their name. And we have lots of globular clusters in our galaxy. They're not unusual in and of themselves. What's weird about this one is how giant it is. A typical globular cluster, whoops, knocked over something. Where's my laser pointer? There it is. A typical globular cluster is this size, the size of just the center part. That's an average size globular cluster. And this is, again, Omega Centauri. It has an estimated 10 million stars and is, about 150 light years in diameter. An average one is, 10 to 20 light years in size. It is a beast. I want to tell you a little bit more about it. I'm going to play this video that shows really, really cool, just panning through some high resolution images of Omega Centauri. Now, the mystery, of course, has been how did we get such a gigantic globular cluster? Globular clusters, we believe, formed in the early universe, where they were kind of the first things to form in galaxies as the galaxy started forming. This one, we actually don't think started out here in our galaxy. We think Omega Centauri is actually the core of a smaller galaxy that the Milky Way ate. And that happens all the time. That's how galaxies have grown to the size we see them today. They start out as smaller, small galaxies merge together and become bigger and bigger. It's normal. It's a normal part of galaxy evolution. So we think that when this small galaxy merged with the Milky Way, its core was able to hold itself together. And that's all we see left of it, that we now classify as a globular cluster, because that's what it resembles now. But yeah, we think that's the remnant of the core of a galaxy that the Milky Way ate, which is pretty cool. And we do see evidence of that. I mean, we see evidence of the Milky Way consuming smaller galaxies all the time. So maybe not, I think it's a really cool solution to it, though, right? It's a galaxy that didn't get fully incorporated, and its core is left behind. All right. For our penultimate stop, we are going to head out of our galaxy into the universe of galaxies. Now, our universe has, we believe, about 2 trillion galaxies in it. And most galaxies come in one of 3 types. You have elliptical galaxies, which are basically galaxy-sized versions of globular clusters. You have spiral galaxies, which is what our Milky Way is. And then everything else is an irregular galaxy. Now, usually irregular galaxies are galaxies that are in the process of interacting or merging. Because as 2 galaxies get near each other, that's really strong gravity is pulling back and forth, and it distorts the shape of the galaxy. Well, the object that we are concerned with, the galaxy we want to take a look at, is Hoag's object. This is what this galaxy looks like. It's weird. Now, we have seen galaxies present as rings before, but that wasn't actually the galaxy shape. That was an effect from what we call gravitational lensing. As the light from the galaxy made its way to Earth, its path got warped by gravity, by all of these really, really massive objects in space. And so by the time the light got to us, the image we get is warped and distorted. Think about like looking at something through the bottom of a glass bottle. Everything gets kind of warped and distorted as you look through it. That is not what this is. That red middle part and the blue ring are all part of the same object. This is what the galaxy actually looks like. And we have no idea how this shape could have formed. Now, the 2 different colors tell us a little bit about the history. The redder center must be an older part of the galaxy, because the red is coming from predominantly red stars, and those are stars that live for very, very long times, whereas blue stars have very short lifetimes. So the blue ring must be younger because you still see those blue stars, but the red center must be older because all of the blue stars have died by now. So somehow you had what started out as probably an elliptical galaxy got a ring of new star formation around it. And yeah, we don't know. We do not understand how an object like this could form. We have found, since we found Hoag's object, a few other galaxies that look similar to this. But yeah, they are pretty rare and relatively a new type of galaxy. So there is a lot of work going into understanding this strange galaxy type that we seem to see every so often amongst the galaxies. All right, for our very last stop, of course, if we're going to talk about strange things in space, we are obviously going to end with black holes. Now, what we're seeing right now is Sagittarius A star. That is the supermassive black hole that sits at the center of our galaxy. Before we talk about supermassive black holes, though, I want to talk about black holes in general. So small black holes, what we call stellar mass black holes, form as the result of the death of massive stars. Really, really big stars. We're talking like 25 times the mass of our sun. When they die, they explode in a supernova. And that core of the star, if it's heavy enough, if it's massive enough, can actually collapse in on itself and creates a black hole. So a black hole is really just so much mass packed into such a small volume that gravity is at its extreme. No matter what you do, you could not travel fast enough to get away from that gravitational pull. Now, that's not true everywhere. black holes kind of get this bad rep of being these like cosmic vacuums that just suck everything up in their path. That's not true. You do have to get a certain distance. You do have to cross what's known as the event horizon, or the path of no, or the point of no return. And that's when gravity is at its extreme and you can no longer escape. As long as you stay out of the event horizon, you're fine. You can get away. So that's a small black hole, a stellar mass black hole. What we see here with Sagittarius A star, as I said, this is a supermassive black hole. This one in particular has about 4 million suns worth of mass. We do not yet know how a black hole this gigantic can form. Originally, we thought that maybe you just have small black holes and they merge together, because black holes can merge together, and then they create a bigger black hole. And this happens over and over and over again until you get this monster. Then we realized that not only does our galaxy have a supermassive black hole at its center, almost all galaxies do. So this must be a standard part of the formation of a galaxy if we see them everywhere. But then, not only are we seeing them in galaxies, we are seeing them in very, very young galaxies. Galaxies that are so young that they should not have had time for a bunch of small baby black holes to merge together to form a supermassive black hole. So there must be some other mechanism that takes place in the process of galaxy formation to make these things. And we don't know yet. That is a very, very active field of research in astronomy. In fact, one of my previous planetarium students, they did their undergrad research looking for kind of the intermediate step, intermediate mass black holes. Because if black holes really do start off forming from small to big, there should be some medium-sized ones in there as well. And so his research was trying to find them. And they did actually find some, which was really interesting, and some of the first intermediate mass black holes that had been ever found. But that does mean that some black holes do form starting small and then growing bigger and bigger and bigger. And yeah, it kind of just added some more mystery, some more questions into what's going on. Yeah, so that is our final mystery. To leave us off, I'm going to show you a couple of pictures. This is a picture of the supermassive black hole at the center of our galaxy. This was taken with the Event Horizon Telescope, which is actually a network of telescopes across the globe. And it is the second ever picture, direct picture of a black hole, with the first being the black hole at the center of the galaxy M87, which you can see here. So the black central part is the black hole itself. That brighter ring of light is the accretion disk, the debris that's slowly spiraling into the black hole, which is in the generated image that we were seeing before. You're seeing that accretion disk. And it's brighter in some places because the disk isn't smooth, it isn't uniform, it's a little clumpy. And so you get some areas that, are a little bit brighter because of that. Yeah, that brings us to the conclusion of our show. Now, obviously, there are many, many, many more bizarre things in the universe. And my goal for this show is to add more over the next few years. But for now, those are the mysteries, the bizarre things, the strange things that we are going to take a look at this evening. But before we head out, are there any questions? No? Okay, my personal opinion, aliens are out there. As I said, in our galaxy, we have an estimated 20 billion Earth-like planets. Of galaxies, we've got an estimated 2 trillion galaxies, each with tens of billions of Earth-like planets. The statistics to me say that there are aliens out there. What they look like, don't know. Will we ever contact them? Don't know. Space is really big. And it takes a long time to travel, even just amongst the closest stars to us. So yeah, I do think they're out there. Whether we'll actually find them or contact them, or if they're even intelligent, don't know. We'll see. Yes. Ooh, good question. What would happen if we fell into a black hole? So as you fell in, your feet would get pulled a little bit faster. So say you jumped in feet first. Your feet would get pulled in a little bit faster than your head, and that would stretch you out. So as you fall into the black hole, you would get stretched. It's what we call spaghettification, because you turn into a noodle as you fall into the black hole. Yes, that is the actual scientific term, spaghettification. It's my favorite term. I love it. No, you don't necessarily. It just means that not even light is fast enough to escape, which is why they're black. But you would not fall at the speed of light. You would fall really fast, but nothing with mass can actually move at the speed of light, because it would take more energy than there is in the universe to make something move even a fraction of the speed of light. Yes. What is past the edge of the universe? We don't know. So there is our observable universe, which is the universe that we see. That's not necessarily the entire universe, because light takes time to travel. So there could be things that are even further away that the light just hasn't gotten to us yet. So it's very possible that from what we see, the universe is actually bigger. And then what's beyond that, no idea. We have no idea. But it's fun to think about. All right. Well, I will still be back here if you have any other questions. Thank you all so much for coming out. Before you head out in front of the TV at the entrance, there are some star charts. Feel free to grab one to take with you. Have a safe trip home and a wonderful rest of your week.